Hey everyone! In this video, we'll try to answer some questions about languages. In hopes to understand which languages are the longest in word length, we'll try to determine the probability of a word being longer than 15 characters in several languages. To do this, we will have to get some data about languages, including the list of words in that language. After we obtain the data, we can try to fit probability distributions and use the built-in probability functions to compute the probability of a random word being longer than 15 characters. With that in mind, let's get started. We already talked about entities before. In this video, we'll be using a specific type of entity, that is, the language entity. Previously, we entered entities through pressing Ctrl plus equals, but we can also directly enter the syntax for an entity. We have our entity function first, then our type of entity or entity class, then the actual entity name, in this case, English. We get back an entity corresponding to the English language. Language entities, like most others, have several properties we can utilize to perform data analysis. We can look at the list of all properties by calling out the properties of our English language entity. Let's look at some of these properties. We'll start with countries that have English as an official language. It looks like quite a lot of countries. There are some surprising ones here, such as Singapore and Sudan. Getting the length of the previous output, indicated by the percent symbol, gives us 35. That's about 15% of all the world's countries. What about English's speakers? Well, there's two kinds: native speakers who grew up with the language, and non-native speakers who learned the language later on. We will use the entity value function and indicate that for the entity English, we want an association with the number of native and non-native speakers. It looks like there's more than 2 times as many non-native speakers as native speakers. In total, it seems that English has over 1 billion speakers worldwide. I now wonder, what languages have the largest number of native speakers? Well, luckily, we can find out easily. We will call the entity class language and then indicate we want the largest 10 in terms of native population. After that, we will denote that we want the list of these entities using entity list. It looks like Mandarin is on top, followed by Spanish, and then English. Let's try one last example. How many Wikipedia articles does English have? What about Spanish? It seems like we have a lot of languages, but just how many are there in our data? We can take the whole entity list of our entity class languages and take its length to find out. I'll also show a shortened list by applying the short function onto my lang variable to see what types of languages we have. It seems like we have a wide variety of languages, most of which I have never even heard of. This is good news on the depth of our data. If we scroll down, we see that we have over 9,000 languages. That's certainly a whole lot. I want to touch on another function we have that contains a lot of data: word list. Word list without an argument simply returns the list of common English words. Let's try to see what the most common letter in the language is. How about this? Let's join all the words together to make some massive string of characters that is the entirety of common English words. From there, let's apply the characters function, which will splice it up into a big list of all the characters in this string. Then, we'll apply the counts function, which will tally up the list of characters. To visualize this, we can generate a word cloud. It looks like E is the most common letter, as the size of letters indicates their frequency. But this isn't exactly the right way to go about it, since we have some non-letter characters such as dashes and also upper and lowercase letters. To counteract this, let's use the function letterCounts. This function does the job of counting the letters in our big combined string. We'll make sure to let it know that it should ignore cases of the letters by setting ignore case to true. We can once again visualize this data using a word cloud. The letter E seems to remain king. Now let's look at all known words, not just the common ones. To do this, we will set up very similar code, But inside the wordless function, we will write that we want, quote, known words, unquote, which digs up all the words we have for English. Once again, we can visualize this data through a word cloud. Perhaps more clearly, we can try to visualize it through a pie chart. It looks like the three vowels, E, A, and I, are dominant, while the most common consonant is R. The least common letter seems to be Q. Interestingly, so far we have only used the letter Q in our script 7 times out of 4,000 characters. This is pretty rare to me. Let's dive into another side adventure, this time involving machine learning. Can we predict a word's language? We definitely can through machine learning. Luckily, there's a built-in classifier for this, language, that does this. We can test it with a word such as juggle. This is an English word. Using the classify function and indicating that we want the classifier quote language unquote, we can input our word in. It predicts the word as English. But, as is known with machine learning, it's always probabilistic. So let's see what other predictions it had and what probabilities they had. I can simply do that by calling the probabilities inside the classify function. I will then generate a word cloud to visualize this. It looks like English is certainly first, but French and Spanish are also close. Now let's try classifying a word that is not actually in any dictionary, but certainly sounds like a certain language. I made up the word jugglify. It's not an actual word, but it certainly sounds like it's English. Inputting that word into our classifier gives us English back, as expected. Let's visualize the other predictions and their respective probabilities again. This time, it's very clear that the prediction is English, with other languages having very low probabilities. One can see this directly in our word cloud too. As is known amongst language learners, the ability to determine which word sounds like a certain language, even when the word is unfamiliar, is a marker for mastery. Apparently, our built-in classifier did just that. We're going to try answering our question now. First, we'll have a list of all languages that we have wordless data for. We'll store this data into our variable languages. I first want to look at the distribution of word lengths across different languages. To do this, I set up an association between the string length of words in a particular language and the language itself. I'm using a pure function here, as indicated by the green hashtag. Pure functions are essentially like the functions you would see in an algebra class, where the variable is an empty hashtag waiting to be filled. I'm using wordlist here and indicating that I want the known words for a particular language. After applying the association map function, this hashtag will be successively replaced with the strings in my list languages, giving us the corresponding distribution of word lengths in each language. To establish a pure function, it is important to have an ampersand, or the and symbol, after the pure function expression ends. To visualize this huge amount of data, I will use a histogram. This will help us see how the word lengths are distributed by language. I will use key-value-map, which maps a particular function onto a set of keys and values in an association. The keys are indicated by hashtag 1 and the values are indicated by hashtag 2. Once again, we're using the syntax of pure functions to help us map a general function onto our data variable. Our data variable has its keys as languages, so we will make our plot label that, and it has its values as the list of word lengths, so we'll make that our argument that we want to make a histogram out of. Inside our histogram, I am indicating that I want it plotted as a PDF, or probability density function. This gives me the probability that a word is a certain length, rather than simply counting the frequency of word lengths. After a bunch of options to clarify our visualizations and arranging them using the multi-column function, I finally have my list of distributions. As you can see, some languages are more symmetric than others. It seems like Faroese is skewed heavily to the left, while Brazilian Portuguese seems to be a very symmetric normal distribution. Now that we have probability distributions visualized, we can try to make an empirical distribution based on the data for each language. Let's start with only English, for example. We will apply the empirical distribution function onto our English data to get this data distribution. I can show this overlaid on our histogram distribution using the show function. Inside the show function, I will plot the probability density histogram and also a discrete plot of my empirical distribution D using the PDF function. To get the probability of a random English word having length more than 15, I can use the n probability function. I will simply state my condition that x is longer than 15 and state the distribution of x follows my data distribution D, which is what this symbol indicates. Let's do this for all languages. We will use the same n probability function with the same criterion, but this time our variable x is distributed according to the empirical distribution of the language we are mapping our function to. Again, we are using the same concept of pure functions. We will take our output and sort it in descending order using the percent symbol, which indicates the last output, and using reverse sort as well. Finally, we will plot a bar chart of this data to visualize it. It looks like German and Finnish are certainly the longest languages, with Danish and Faroese being also close. Hebrew and Arabic seem to have very few long words in our data. It looks like Germanic and Uralic languages are the longest. Romance languages are in the middle, and Semitic languages are the shortest. This analysis could be easily extended and can make for really interesting comparisons between language families. Go out there and explore the world computationally.